Good, so let's move on to the zeta function. That's the most weird and fantastic part of the course. I wish I could spend more time on it. But last time, actually, I did none of what I'm going to do today. So that's new. Particularly, it means that there may be typos. But we'll see, okay? Good, so really what's going on here, I mean, this is like an awe. You should have an awe looking at this title. Because unless I'm crazy, I'm telling you that we're going to kind of talk about the proof of the Riemann hypothesis. Like sign for I should retire. But over function field, it turns out this is a theorem. It's the Hasse-Weil theorem, Hasse-Weil bound. Hasse proved it for some cases, but built a lot of the machinery and theory. And then Weil kind of closed the theorem completely and proved it for all function fields. But we'll see what do I mean by that even. I need to tell you what do I mean by the Riemann hypothesis for function fields. Okay, so let's start slowly, and I'm going to go slower now. So throughout this unit, we are going to fix a field fq. Q is some prime power. It could be like just a prime, that's fine. But Q is going to be the prime power, P is going to be the characteristic. The genus is going to be G, and just as a reminder, the set of prime divisors was denoted a long time ago like that. Now, I don't know if you remember that, but these are notations that I need today and we haven't used for quite some time. So this Mafcal D is the set of all divisors of the function field, and the group of principal divisors is this group. You take every non-zero element, you look at the principal divisor, that's what you get. And we, for a short while talked about the divisor class group, namely we take all divisors, which is a group, and consider the quotient by this subgroup. And by that I mean really, I'm looking at a divisor, modding out and identifying every divisor with it plus some principal divisor. And the reason I'm doing that, we'll see today even more, but the reason I'm doing that is because the degree and dimension doesn't care. Degree and dimension of a divisor is actually a property of the class it lives in. So if you care about those, then that's a good thing to do. Now, I'm going to skip very simple lemmas, but I'm going to just state them. So first of all I care about here is this definition, but let me also talk about SM. So for any integer that you would give me, could be negative. Let's denote by SM, which you will never see again. So for a second, SM is all prime divisors which have degree at most m. And CM is going to be all divisors of degree exactly m, but you mod out by the principal divisors. Okay, so I care about CM. In particular, if you think about C0, what it means. So C0 are all divisors which have degree 0. Now we know that all principal divisors have degree 0. But when I look at C0, I'm asking, like in a sense, how many more divisors have degree 0 compared to the principal ones? Because I'm looking at the quotient. So H, that's called the class number, it's an important parameter, is the size of this set. And this definition is accompanied by a lemma that tells you that that's finite. So what I'm saying is that CM, also SM, but that's just a tool for me, so I don't care. CM, like if you look at all degree m divisors, I'm going to use it again and again, so let me write it here. So CM, you look at all divisors of degree m, but you mod out by P. Sorry, what?
Set above P is not given in book, so what does the formula mean?
Yeah, that's maybe a coset or something. Yeah, as a set. You're right, yeah. It's not when the degree is 0, it's okay, but right. So when the degree is m, yeah, good. Yeah. So as just as the set theoretic clear. Yes, good. So I mean, when you take two such divisors and multiply, you get degree like 2m or whatever. And but set theoretic, that's a partition of all divisors that according to P, and these are all. This is a set, and I'm claiming that that set is finite. It's very easy to do if I'm not going to do it. And I'm going to denote by H the size of C0. Okay. So for example, what do you think H is for the rational function field? Yeah, the right 0, 1. Yeah, good. Because it's 1 because like, In the rational function field, that's what you proved with Tomer, I think, maybe. All divisor of degree 0 are principal. Maybe you didn't do it, but it's very easy to do. Did you do it? 0, right. Yeah, exactly. Right, not only 4, yeah. Good, so the proof is very easy. It could be an exercise when we talked like in the maybe 5th week about these things. It's very simple. So it's written here if you want to look at it. I mean, it's not completely like, it's like, you'll sit about it for like 10 minutes and you'll do it. But we have done it. We have more interesting things ahead. So now we are going to look at a parameter which actually looks weird. So the del, I think it's called the del. I don't know, but I think so. The literature is kind of, but the del of a function field is going to be the following. You're going to ask, I'm looking at all positive divisors, it's not positive, like the degree positive divisors. Positive means that the divisor itself is positive. I mean, just the degree is positive. And I'm asking what's the minimal degree I can get like that. So what is your hunch? Like, what should it be? Should be 1. I don't know. Why shouldn't it be 1? Right? Why shouldn't you get like a degree 1 divisor? Like when we started this whole thing, we normalized everything correctly with the valuations and stuff. It should be 1, and it is 1. But it's not easy to see at all. We're going to prove that on the way. It's actually a fantastic proof of that. So it turns out that in any function field, you have some divisor, not necessarily prime, but you have some divisor, which is the non-negative, like degree is positive, and it's not just positive, it's 1. So you can get all degrees like that. I mean, once you have a degree 1 divisor, you also have a degree 2 divisor and degree 3 divisor. Just take a multiple of it. But it turns out that this is it's 1. We'll prove that later. But what I just said, this claim, which is a very simple claim, tells you that every divisor, once you know that you have a divisor of this degree, you can cook up divisor of multiples of that degree. Obviously, just take the product by like 4 if you want to get 4 del, and nothing else. Because if you had some other divisor with some degree that's not a multiple of that, you can, using like remainder, like a quotient with remainder, you can get a divisor which has degree smaller than that. Right? If del is 4, and you find some divisor of degree 7, then you can cook up a divisor of degree 3. Just subtracting 2 divisors to get the degrees. The proof is written afterwards, but I'm not going to do it. So anyhow, what I'm saying is that this is kind of the regularity. So once you know del, you know all divisors have degree which divides del, and you have all of those. And actually, maybe slightly less trivial, but still very simple, is that we define C0, the size of C0 to be H, or we define H to be the size of C0, and it turns out that actually it doesn't matter. So for every degree for which there is a divisor, namely a multiple of del, the class group has the same size. It's also H. Just there is a bijection, a simple bijection. Just if you look at C0 and you want to understand Cn, so you just take some divisor, if it exists, of degree n, and it gives you an easy bijection between this set and C0. Just like once you have a divisor, you can shift it back and forth. Of course, if there is no divisor, then Cn is 0 of degree n. So Cn is of size h when del divides n, and otherwise it's empty. The size is 0. Okay? And why is 3 true? I mean, what is 2g minus 2? Like, what's the number? Exactly, yes, good. So that's the degree of the canonical divisor. We know there is a divisor of that degree. And so by 1, we know that del divides that. Yeah, fantastic. Of course, del is 1, so that's not really, but at the end of the day, it's 1, not at the beginning. Okay. So that's an easy claim. Again, the proof appears here, but I won't insult you. It's like you see, that's all the proof for all of the claims together. Okay. So with that, let's, actually kind of orthogonal to that, let's take a divisor A and ask the following question. That's going to be a very important question for us. Very simple one, but you can ask how many non-negative divisors, not just degree, actually they are as divisors non-negative, are there that are in the same class as A? congruent to A. So the number is going to be that maybe, I don't know, expression that you see there. It's q to the dimension of the corresponding Riemann-Roch space of A minus 1 divided by q minus 1. And the number also almost give you the proof, because you look at this number, you say, I mean, if we learned anything at this point, we know that once you have a number, you should find an object that has this size or whatever. And this is I kind of almost know what it is. So if you are familiar with projective, and when that's something was projected here, and so let's see. So the reason that's true, and again, I'm just sketching it, it's very short anyhow. Let's look at the following set. So I'm going to take the Riemann-Roch space of A, exclude 0, and look at the principal divisor corresponding to it. Okay, so just look at this set for a second, stare at it. You'll see, first of all, that if I take two x's that just differ by an element in FQ, like x and 2x, they're going to give me the same thing, because the principal divisor doesn't change when you multiply by a constant. So that's kind of the reason for the q minus 1 at the denominator. So for every element here, so the size of this set is, I mean, this has a dimension dim A. So as a size set, it has size q to the dimension of A, well, over FQ. So this is q to the dimension of A minus 1. And what I'm claiming is that every element that I counted here, I should count only up to scaling from FQ, non-zero scaling, so I'm dividing by q minus 1. So the size of this set is precisely that. Again, because this is q to the dimension, q dimension minus 1, and I'm not looking at those, I'm looking at those corresponding principal divisors, and they don't mind the, whatever c multiplies x, c from FQ that's not 0. I mean, you can't multiply by 0 because then you get 0, and 0 it doesn't have a principal divisor. So what we just said was that the right-hand side has this, the right-hand side is the size of this set. So in order to prove that, we just need to find a bijection between this set and that set. And okay, so why is it true? So let's start from the left. So if you take any b, so A is fixed. If you take any b which is congruent to A, like it's in the same class, then kind of by definition, it means that you can write it like that. Right, b is A plus some principal divisor. X, of course, is a non-zero element because you can't principal a zero element, the zero element. So that's generally true, regardless of the assumption that b is at least 0, just generally speaking. But because b is at least 0 as a divisor, then we know that this means that x, this is at least 0. So this means that x is in the Riemann-Roch space of A. And that's kind of saying that this is at least 0 is saying that x is in the Riemann-Roch space of A. Good. So and now in the other direction, if you give me an x in the Riemann-Roch space which is not 0, let's define b to be A plus x. I mean, A is given. So b to be A plus x, it's non-negative because x is in the Riemann-Roch space of A. And clearly b and A are congruent to each other because b is A plus x, which gives the other direction. You should just look at it for a second, making sure the normalization is okay, but that's fine. Good. And before the break, let me just define this thing. So, or just reformulate lemma 5. So in lemma 5, what I did, it was nice for the proof, but it's not nice to continue on. I look at a class by looking at a representative. So I took an A, and I ask, what's the class size of A? At least, when I take all just non-negative divisors there. But it's nicer to do the following. It's nicer to take a class, C, in the class group, not an A, just the class itself, and ask how many elements, like divisors, in the class do I have which are non-negative? The same question. The previous question, I just took an A from the class in order to kind of study that. And of course, the dimension of C, when I write dimension of C, I write the dimension of the class. What I mean is the dimension of every element in the class. Right, so that's what's written here. The dimension of a class, the class is just a bunch of divisors. But it's like the dimension which is common to all elements in the class. I don't show I use that notation. I'm using it here. And I'm just kind of writing what we said before in terms of C itself, not a representative from C. Right, and after the break, we're going to like 2 slides away from defining the zeta function of a function field, or 3 depending if you count the first one. Good. So we have a break. We have sugar, a lot of sugar from different places. Maybe I ate half a cookie on the way, but yeah, okay. Okay, so maybe we should continue. Okay, so far, just as a recap, we proved that if you take a class, a divisor class, then it's going to have infinitely many elements, but the non-negative divisors there are going to have precisely this size. It depends exactly like that in the dimension of the class. Is it okay? I mean, we do need that, so yeah, maybe I just write it here below the definition. I mean, it's going to be reminded all the time, but just so that you have in mind. So all B in C, B non-zero, the size of that, which is Q to the dimension of C, which is the dimension of every element in the divisor divided by Q minus 1. Oh, sorry. And what I care most about is actually this quantity, AN. I'm going to relate it to what we did, but AN. So what is AN? So for a non-negative integer, AN is simply the question, how many non-negative divisors do you have which have degree n? Degree in a sense is a notion of size. So how many size n divisor do you have? But you have to take the non-negative ones. It's like in integers, like how many numbers you have of size 5. So you have 2, like 5 and minus 5. But you check it's only 5, and that's how you do it. Here it's going to be not twice, but like infinitely many. So you're going to do it like that. So AN is exactly those, this is a very interesting sequence. Like how many divisors do you have of degree n? Again, a negative ones. And from what we just did, we can count this AN used by classes. So namely, if you want to count AN and C, like Cn, like capital, like this Kmafkal C was all of the classes. Cn was all of the classes in which the divisors there have degree n. I don't even know if, yeah, I did that. That's there, yeah, sorry. And you can kind of count AN by classes. And then you can go class by class, and we know how many divisors we have in each class. That's what's written there. For every C, you look at all the negative divisor. So if you want to count all of the divisors of degree n, you can just do it class by class. And it's nice because in each particular class, the number is precisely kind of determined by the dimension. So that's AN. We really care much about this sequence. You'll see why. So according to what we did, actually we know that AN is either 0. It's not like, I mean, it is mysterious, but it's not that mysterious. It's 0 when n is not a multiple of del, because we said when you are not a multiple of del, there are no divisors of the degree. And when you are a multiple of del, well, I don't know, it's kind of, who knows? But when n is larger than 2g minus 2, we know that at this range, the dimension is precisely the degree minus g plus 1, Riemann-Roch. And so we can write AN like that, at least for n which is larger than 2g minus 2. So when del divides n and n is large enough, so it's h. Why h? Because this is how many summons you have here. We said that the number of elements in Cn is the same as the number of elements in C0, which is h. So it's a sum, but it's not really a sum. It's just h times this. If the sum is non-empty, it's h times whatever it's written there. And that's exactly what I wrote there. I wrote into h times. Instead of writing q to the dimension, I wrote n plus 1 minus g, because that's the dimension when n is large enough. So AN, sorry, it is mysterious. But AN, at least for n large enough, it's not so mysterious. Okay. Questions? And I also need one more definition before showing you the zeta function and its friend, the z function. So the norm of a divisor is going to be q to the degree of the divisor. If you think about it, ignore one for a second, that's precisely the size of the residue field well, for P prime, it's the size of the residue field of P, right? Because the residue field of when the divisor A is just a P, like 1 times P, then Q to the degree of little p is precisely the size of the residue field, because the residue field has degree P, so size Q to the degree of P. So the norm actually captures something about the residual degree. And what's nice about it, we are going to use it kind of implicitly, is that it's multiplicative, right? The norm of A plus B is the norm of A times the norm of B, kind of obviously, because you just add the norms, the degrees. So with that, I can actually finally talk about the zeta function and its z function, which is actually easier to work with. Okay. So what is the zeta function of a function field? Good. So how many of you know like what is analytic continuation and stuff like that? Okay. We don't need that much, but I may say a word or two about it at some point, but don't worry about it. So the zeta function of a function field is essentially what it tries to do more or less is to be the generating function for the sequence A0, A1, A2, and so forth. But let me define it first in the usual way. So the zeta function, denoted by like cool zeta of s, it's a complex value function. So think of s as a complex number. And what you're going to do is you're going to iterate over all non-negative divisors, not just prime divisors, all divisors. And you look at the reciprocal of its norm to the s. Okay, so that's this thing. And because of what we just said, because the norm of an element by definition, going backwards, because the norm of an element is just q to its degree, you can also write it like that. Instead of writing the norm, you can just write q to the minus s times the degree of a. Now, if you know, do you know about the zeta function, like the usual zeta function? Like, anyone never saw it before? You've seen it. Good, yeah, good. So the zeta function in general, like the Riemann zeta function, that's actually the Artin function. You define it later, but the zeta function is this expression. Like, you look at the reciprocal of n to the s, where s is a complex value number, and you really care about where the zeros of this function looks like after you extend it analytically in a sense. Never mind that for a second, we are going to get to that. But you see, it's a very similar looking expression at least. So here you go over all non-negative numbers. Here you go over all non-negative divisors. Here you take kind of the size of n, which is just n, to the s. And here you take the size of the divisor a to the s. That turns out to be the right notion. You will see why. Like it's an analog, okay? It's not this. It has no effect whatsoever on one another, but it's the right analog. Coming up with the right analog is very important to do. So that's the zeta function. It is actually nicer, at least for us, I mean, depending what you do, but today it will be nicer for us to actually, instead of looking at the right-hand side with q to the minus s, which is weird, like why are you looking at q to the minus s if you... So instead, we are going to consider this as a function in t, which is q to the minus s, just a change of names, like really. So you can define z of t, so that's the z function, like it's a cool z like that. Z of t is zeta of s, where t is q to the minus s, just kind of plug and play. And if you look at it for a second, on the right-hand side, you get that z of t, again, you sum over all non-negative divisors, but you take t to the degree. That's what you do. And if you do that, and it's just going to be, I mean, it's the same, there's no difference between the two, it's just nicer in our context. And if you do that, then instead of just going over all divisors and sum up t to the degree of that particular divisor, you can bunch them up according to the common degree. Because we know that we didn't prove, but I said that there are only finitely many divisors, non-negative divisors of a given degree. So you can do that. And indeed, how many divisors of degree n are there? That was the definition of an. Right, so n, which appeared before, is how many divisors do you have of degree n, which are non-negative. So I'm just, putting them together in this sum, like that. So that's what I said. The z function, not really the zeta function, but the z function is the generating function for this sequence. Questions? Because that's going to be important for us. Okay. So here is a theorem. It's going to be like crazy now, like in terms of interest. I mean, like yeah, it's kind of amazing how each click is going to be like crazy. So I don't know, maybe just me. So first of all, you look at the Zeta function, right? Just this one, and it's written as a formal series. And I don't know if you know about too much about like generating function and stuff, but the key idea every time when you do that is to you have a sequence, you consider the generating function like that, and then what you want to do is to find a kind of compact representation of it. Like for example, the sum of t to the n is just 1 over 1 minus t. Right? That's a compact representation. It's a compact representation that it's not always true. Like sum over 2 to the n is 1 divided 1 minus t. So that's an identity which formally does hold in a certain ring, like a ring of formal power series or whatever. But it actually also holds true like as a complex value function. Right? At least as long as this is defined. Like if you start from here and you start from here and say, oh, I know that's this thing, then what you really mean is that for t with modulus smaller than 1, that equality holds. But then what you can do is you can look at this thing and you can say, oh, but this thing is defined even when this is not defined. Right? So this is not defined when t equals 2, but this is defined at t equals 2. It's defined everywhere except for t equals 1. So you start with some formal power series. You don't think about where it's defined or ill-defined. You note sometimes maybe that you can have a compact representation of it. Those who took free probability last semester saw that already. And when you look at this thing and you try to understand it as a complex value function, like where it is defined, holomorphic, blah, 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 don't worry if you don't know what that is. But the point is that this is, in a sense, the only extension of that thing. So, I mean, I told you that these are equal because we know something about geometric power series and so forth. But it turns out that there is only one way to extend this function, which is only defined when t is close to 0, like most 1, to this. This is another, it's called analytic or differential function in some domain. There's only one way of doing that. So actually, this function is that function. It's defined in places in which this a priori wasn't defined, but it actually was. You just looked at it locally and in the wrong way. Right, so that's what analytic continuation is. To start with a formal power series, try to compactify it, like not in a math sense, just like write a small expression for it. Look at it as a complex value function and use complex analysis to understand it and infer back about the series that you have. That's what's going to happen now. But it's very light on what you need from complex analysis, so don't worry. I mean, what we are going to do is very light. So anyhow, what I just, in our case, we don't have the sequence 1, 1, 1, 1. We have the sequence A0, A1, A2, A3, and so forth. So you would expect, a more complicated expression here than 1 divided by 1 minus t. It somehow should encode, the entire function field in a sense, like at least the information about how many divisors you have every degree. And actually, you might be surprised that there is a compact way of writing it, because the AIs are strange. But there is a way, and the reason there is a way is because that it's actually quite regular when n is above 2g minus 2, right, as we said. The only weird thing happens at the beginning, and after the 2g minus 2, we know kind of everything we'd want to know. We know exactly what an is, right? It's like going backwards, this is an when n is large. I mean, we don't know del, but other than that, we know that it's exactly this expression, O0. So that's why it's not kind of magical that there is a compact way of writing that. And what is the compact way? So it turns out it depends if you look at genus 0 and genus non-zero. So this is the theorem. So the theorem is that the z function, should I write it somewhere? So the z function, just the generating function for the ANs, where the ANs are how many divisors you have of every degree, which are non-negative. So the z function for is defined. So again, I want to talk about it as a complex value function. So it is converges when t is smaller than 1 over q. We'll see why. And therefore, the zeta function converges when the real part is large enough. Don't worry about it. And actually, I can give you the expressions. Like I can give you the 1 divided by 1 minus t, which is easier to see. So for genus 0, like the rational function field, essentially, this is the z function. looks like it's 1, I don't know, you should stare at it for a second. It's 1 divided by q minus 1. It's a rational function like this one. Depends on q and del. Okay, whatever. And for g, which is larger than 1, you would expect to see something about the genus floating around, and indeed. So the z function, it turns out you can write, okay, there is this 1 over q minus 1, but then you can write it as a polynomial. So if it is going to be a polynomial, we'll look at it in a second. That's the interesting part. That's what happens below the genus, plus a rational function. And actually, you can take away an h from it, the size of C0. And so what is the polynomial? So that's the interesting part. So the polynomial, you go over all classes of degree at most 2g minus 2. That's the irregular part. And the polynomial is, the coefficient of t to the degree of c is q to the dimension of c. Okay. And for the rational function, you get kind of a fairly closed rational function. So it's like you have all of the weird, it looks like someone's just spit all the g's, del, q's, and t there, but it's q to the 1 minus g, q to the whatever, what's written there. Okay. Okay, so it's a lot to take, but it's just like there are expressions like that. Why is it true? Let's do it. So first of all, I said that it converges for t smaller than q minus to the q minus 1, and therefore zeta converges for the real is larger than 1. Don't worry too much about it. It's just because t is q to the minus s. So when t is and the size of q to the minus s is q to the minus real of s. If you don't know complex analysis much, then you need to remind yourself of these things. So I don't want to worry too much about it. But just saying that t is smaller than q minus 1 is exactly the same thing as saying that the real part of s is larger than 1. Right? The imaginary doesn't affect the size, just the angle. So. But don't worry about that. So let's do the g equals 0 case, just so that you get acquainted with that. So I want to prove this thing. So why is it true? So let's start with zt. What is zt? By definition, that's what's written here, is just this formal power series, the generating function for the sequence an. But we know from one of the equations that you only have degree n divisors when they are divisible by del. So I can just go over, I wrote it as k, but k goes from 0 to infinity, a del k, t to the del k. Right, and I'm actually using the fact that everything is simple. So this equation holds from 2g minus 2, but when g is 0, it's everywhere. It's just always the case. So we know for the rational function field, or for genus 0 function fields, we know exactly what's the relation between the dimension and degree. Just dimension is degree plus 1. Right, so I'm using it here because that's why it's so simple. So I just wrote, I should write like, yeah, okay, that's just that. And now I know that a del of k is precisely this thing. There is nothing weird about going on. So you see, this is the degree plus 1. This is the dimension of a degree del k divisor. And for me, it's just like two geometric series that you collapse together. So you take the q minus 1 from the numerator outside, and then you sum up this and that separately. Right, so you have 1 over q minus 1, and then in this expression, you can take one more q outside, and you left with q times t to the del k, which is just a very simple, this is essentially the 1 divided by 1 that we have. And here you have the minus 1 over q minus 1, and it's the same thing, just shuffling things. What about the larger genus case? So that's more interesting. So let's see. So zt is, again, the generating function for the sequence. And now I want to break it. So I'm going to break an according to, like we did before, to the classes in Cn. I count the degree n divisors according to the classes. So for every particular n, we said that this is an. Right, that was an equation from before. Yeah, it's this thing. You can just sum up according to the classes. So that's what's written here. And then again, I'm taking q minus 1 outside, like the 1 over q minus 1 outside. And then I separate the q to the dim and the -1. Oh, actually, no. First of all, I take the q minus 1 side, and then I separate n from 0 up to 2g minus 2. That's the irregular, interesting part, and then the larger n's. So when n is between 0 and 2 to g minus 2, I just write I just write this thing without the -1. The -1 I actually do take outside, sorry. So forget about the -1. It's not there. Also, the q minus 1 is not there because of that. And then you have, you have this expression, q to the dim, c to the n. The -1, I do all of them together. This is this expression. You stare at it for a second. And without the -1, the n goes from 2g minus 1 up to infinity is written here. And you see you have q to the n plus 1 minus g. Why could I change the dimension of c to that number? You see here I kept it, but here I replaced it. Riemann Roch, exactly. Once the dimension is large, a degree is large, you know the dimension. It's the dimension plus 1 minus g. N plus 1 minus g. Right, and if you stare at it for a second, you have a polynomial here. That's a polynomial. That's going to be ft. It's a degree at most 2g minus 2 polynomial in t. And then the other part is not a polynomial. I don't know what it is. We are going to do it in a second, but it's still like infinite sequences like that, but they are very regular. You can see that you can make a thing like that again for those, because everything is very simple. It depends only on the index, not on the dimension of some weird thing. And indeed, you can write f of t. So this you can write. So f of t is this polynomial that we wrote here. And actually, maybe let me just massage ft a little bit more. So f of t is this polynomial. So the q minus 1 is outside. And instead of, before it was useful for me, but now, instead of summing over n's and then over c and cn, I just want to do it like to sum over all classes, like separate all classes without separating to n. So I'm going over all classes of degree at most 2g minus 2, because that's the n that appears here, the degree. And then I sum q to the dimension, t to the degree. So if you remember, going to the statement, so I told you that you can write the z function. Well, there is this expression going outside, and then there is a polynomial f of t, and that was indeed a polynomial. Now, as for the rational function, so the rational function is so g of t. So let me go back and tell you what I'm doing. So this is f, forget about it. Now I want to write g, and I promised you I want to write it as 1 over q minus 1, that's here, plus h times g. So that's actually g over h. Okay, what's written here is going to be g over h, because I want the h to be outside, you'll see why. So I'm copying that, but that you will see divided by h every time. Those two. So that's g. Well, note I also kind of flipped. So I don't know, it doesn't help to do like that. But here in g, forget about h, you have a sum over n, and then you have a sum over c's. But I told you that this sum is not really a sum, it's just how many elements you have in Cn. Right, because the sum, the number of elements in Cn is the same regardless of n. It's either 0 or h, or Cn. So that's what's written here. So instead of having a sum of Cn summands, I just wrote Cn divided by h, and then q to the n plus 1 minus g times t to the n, it was what's written here. Anyhow, I'm going back and forth, and the other expression is the same. Again, going back, I'm just doing the same thing for here. It's t to the n over h times Cn. And we said that Cn and h are the same. So I just, Cn and h are the same when Cn is not empty. Sometimes it's empty when it's not a multiple of del. So anyhow, you can actually, so you can take the q to the 1 minus g outside here. Then you'll be left with q times t to the n, which is nice. And the n's that you have to sum over are only those that are divisible by del. And when you do have a contribution from them, this is 1. That's why I wanted the h there. Because ch is cn if h in size. And so what are the n's that survive? Those that are divisible by del. And I'm starting from 2g minus 1 here. So it's nice to write it like that. So n starts from 2g minus 2 plus del, because, we said that this is this is divisible by del. So this is the first number that is divisible by del that's larger or equal than that. Because there is just one. It's a little bit of a nuance here. And the same nuance happens there, but without all of these q and g's, just t to the n, the same expression, starting from 0 though. And then you have like the usual thing that we have here, two like geometric series. They don't, one of them doesn't start from 0, but whatever. So you get this expression, which you can stare at for a second if you want. Questions? I know it's like, but the slides don't help here, but question? Yes.
You don't understand like the math, but it's from
Yeah. Yeah, well, you'll see in a second. I still can't do that. Yeah, you'll see in a second. Yeah. It's very short, it's coming shortly, so that's fine. Actually, maybe now. I mean, it's the general question is why should I look at generating functions as complex value function, and what will it? I mean, what is it useful for? In particular for this context, right? Good. So just as a recap, I mean, I'm not. I am going to answer your question. Like, actually, that's going to be the 1.5 hours that are coming. But the z function can be written as a 1 over q minus 1. Don't worry about that. A polynomial plus h time a very regular expression. It's regular in the sense that it depends only on g and del and q, like things we kind of know, more or less. Not on like, f is more interesting. I don't know how many, what's going on below the genus because I don't have a Riemann Roch there. But just as a corollary, when you stare at it, and that's what I mean by analytic continuation, when you stare at this thing, you know that this is defined when t is, you know that this is defined when t is smaller than 1. Because you know that this is defined at 0. And the only place you start to see a problem when you go away from 0, at 0, is when t is 1. So the same thing is happening there. So as a corollary, just by looking at these expressions, again, as looking at that expression, you can see that zt, it's a polynomial, f of t. That's fine. It's not going to have any problem in the complex plane. I mean, it's infinity at infinity, but we don't talk about that. And gt does have problems. I mean, it has poles, right? At t equals, at del roots of 1 of the unit, it has a pole here. And also at 1 over q times del root of a unit. Like, if there is 5, a fifth root of unity, That's where the poles are. And this is closer to the origin. Like it's 1 over q in size, the problems here. So we can see that the z function is indeed defined when the modulus of t is strictly smaller than 1 over q. Because only when you get to 1 over q, you get to see a pole. And these are these poles. You get to see del poles together. Like if you move like that. Do you understand what I mean by that? I mean, right, if here we have another expression which happens there, like 1 over 1 minus, I don't know, 2t, when at t equals half, you're going to have a problem here. Right, so also at 1, but already at half. So that's what's happening here. At 1 over q, you get a problem. The del doesn't matter. It just means that the problem is not at the real axis, but also at the real maybe, but at the del roots of unities. Anyhow, and if you think about the relation between t and q to the minus s, it means that the zeta function is defined when the real value is larger than 1. Okay, because it's q to the minus s. So the s is the 1 there. Good, and this line tells you that you can make a continuing analytic continuation of the z function or the zeta function, and that's how you can define functions that are seemingly undefined in places where they actually were always defined, but you looked at it in the wrong way. But I won't get into it because I don't assume you know these things. What is important for us is that, I don't know if you know, but there is this Euler product formula that tells you that the zeta function that we talked about, like not us, like people talk about in over z, which like talk about just integers, can actually be written as an infinite product rather than infinite sum concerning primes. That's why we care about the Riemann zeta function, because there is this relation. It encodes things about the primes, and it's kind of, aside from the convergence issue, it's obvious. Because this thing is like 1, for every p, it's 1 plus, p to the minus s plus p to the minus 2s and so forth. And because you have unique factorizations of numbers to primes, then again, up to convergence issues, then you have equalities here. So this is the usual zeta function. This is like the other way of looking at it. This is with integers. This is with primes. We extended that to divisors, non-negative divisors. So we want to have an Euler product formula with prime divisors. And that's what's written there. So it turns out that, again, up to convergence issue. So when things are converging, like what we did now, when t is smaller than q minus 1, or when the real part of s is larger than 1, you can actually extend similarly by the same reasoning, really. You can write zt, which was exactly that with the norm of s appearing here, or of t to the degree and so forth, to be this product. When you go only over prime divisors, much like you have prime numbers here, and you look at the same expression. Oh, I think maybe I'm missing a... No, it's fine. It's always confusing. Yeah, it's fine. I wasn't sure if I'm missing a minus here. I'm still not sure, but I think it's okay. No, it's fine. Yeah, good. Yeah. So you can do that. I mean, there is a proof afterwards, so I couldn't have messed it up too much. So you can do that. It's the same thing. You say, well, like here, every integer is a product of prime divisors, finite product. That's why you don't have issues with infinite products, because every particular n is a product of finitely many primes. Same here. Every divisor is just a sum. It's in the exponent. Is a sum of finitely many prime divisors. That's the same proof. Will work, but you have these expressions, okay? I'm not going to prove it. It's like just this kind of obvious. I mean, if you know how to do this, then you know how to do it. And what's remarkable is that we can prove using analytic ideas that del is 1. Like the del that we kind of annoyed us. It's kind of an algebraic thing, but I'm not aware of an algebraic proof for that. You need an analytic proof for that. That's called Schmidt's theorem. Actually, Schmidt did much more than that, but I don't know why that particular contribution was named after him. So he actually proved that del is 1, and the proof is kind of fantastic because it's weird. Like, you would imagine something about function fields, and now it's going to be like counting poles. So in order to prove that, I need 3 hours, okay, to talk about a unit I didn't talk about, which is the constant field extensions. So I'm going to slide it through and just state this lemma. It's a very easy to digest lemma, but its proof actually relies on the 3 hours. But you have to just trust me about that. These are 3 courses, okay? So we're doing 2 at the time of 1, and 1 of them is omitted. That's what's going to happen here. But I think the theorem statement is, I mean, it's not obvious at all, but you can understand what it means easily. So it tells you that, but I still have to have the notation. So maybe I'll do it on the board for a second. So we talked about it very shortly last time. So say you have a function field. I called it K there, maybe FQ. Okay. Say you have some function field f over FQ, f of xy over FQ and so forth. This is capital F, this is capital K. And sometimes for coding theory, you don't want to do it, but sometimes you would want to extend this function field by adding constants. Namely, consider an extension of FQ to the R, and then you're going to look at this function field. Namely, usually when you extend function fields, you extend them by adding a new x, like a transcendental element. Here I'm doing the reverse thing, adding just new square roots and stuff like that of constants, like f5, f25. So it turns out that if you start with this function field and you end up with that, I used it last time to talk about ramification. I told you that you don't have ramification in constant field extensions. That's a constant field extension. So it turns out first of all, it turns out that this is a function field, which is not obvious, and I forgot to say it last time. It's like 2 hours of the free. It's not obvious because who said that when you add more constants, well, you do get an extension, but who said that you don't get more constants? Like maybe when you add to fq to the r, maybe here you get fq to the 2r or something. Could happen, doesn't happen. And potentially it could happen. Potentially you would imagine a very simple proof, not easy. But that's a function field. That is indeed the constant field of that function field. And what we know how to do is prove that everything stays the same. Like the genus of that is the same as the genus of that, and everything is the same. Okay? I mean, we can talk about it, but I don't need all of that. And here I talked about the degrees of something. It's useful in the proof of the theorem I'm going to say now. But for our purposes, all I need is the following. So let's say that z sub r is the z function, not of f over k, but f over k after you extended the constant field extensions by like q to the r. So you add fq to the r to f. So when I write fr, I mean f composed with fq to the r. So you add more constants. Smallest field that contains both. Or if you add some equation that you cared about, y squared equals x cubed minus x, it's the same equation, but now you have more constants to work with. So it turns out that there is a fantastic relation between the z function of the r extension and the original z function, like of the non-extended function field. And it's as follows. So it's not expected, I would guess, I don't know. But it turns out that if you are going to evaluate the extended z function, zr, at t to the r, as just a formal element, t to the r, then it's going to be the same as if you're going to only evaluate the original z function at r roots of unity times t for all of those r roots of unity. You take the product. So for example, z2 of t squared is kind of z of t times z of minus t, because minus 1 and 1 are the second roots of unity. Very strange, quite deep. I mean, it's very easy proof given those things that I didn't talk about, but I can do it. So it's here if you want to look at it. But don't worry about that. We have to take it as is. But from here, just assuming this equation, so maybe let me write it because I'm going to use it in a second. So this is quite dead. So from here, we are going to prove that del is 1 using that. And again, the proof of that is extremely algebraic. Like you should have that in mind. A lot of Galois stuff going on. Del is extremely algebraic, and nonetheless, we are going to use analytic arguments to prove that del is 1. So what do we know? So we know that z of t, like generally speaking, is written like that, right? Generally, z of t is just the generating function for the ANs, but we know that the ANs are always divisible by del, so you can write it like that. Now, if you look at it for a second, and you're going to plug a del, I mean, you know the del is 1, but you don't know that yet. So, and you're going to plug in a del root of unity, zeta, to here, you'll see that nothing changes, right? Because it's always taken to the del power. So z of zeta t is just the same as z of t. Right? There's nothing changes there, because you only have t to the del power. So on one hand, you know that z of zeta to the t is z to the t for every zeta which is on del power. So what does it mean about this thing? For r which is del. Right, so this is always z to the zt. It doesn't change. It doesn't care about zeta when zeta is a del root of unity. So it's just a product of the same thing del times. For different r's, it's not, but for particular the choice of del, you have this equality because they're all the same. So that's what's written here. Zeta del to the t to the del is zeta t to the del. And then if you stare at it for a second, you're done. Because when t equals 1, So look at this part. When t equals 1, without the del, z of t has this function, when at t, around t equals 1, it has a pole of order 1. I didn't say it, but it's a pole of order 1, because you had 1 minus t there, not 1 minus t squared. And so this function, what's the pole order of that function at 1? Del, right? Because you have 1 divided by minus t to the del. So 1 has a pole, this function has pole order 1, del at 1. And this function, well, you know, it seems like also del, but it's not, because t to the del is like just when t goes to 1, this also goes to 1. And this function has pole order 1 at 1, therefore. So just because of this pole consideration, it means that del has to be 1. It's kind of crazy, I don't know, right? It's like you're not I mean, come on, that's crazy. I mean, there is nothing algebraic about it. I don't know how to prove it algebraically, and you had to do like kind of not analytic continuation, but analytic considerations to do that. Anyhow, you have that. So we know that del is 1. Only now we can finally clean the equation. So that's the corollary. It just tells you, you know, the equations that we had before, just remove the del, and everything's fine. Like put 1 instead. So for example, for genus 0, we had some expression. I don't really remember what was there. But after you remove the dels, you get this equation. Okay. And for genus that's larger than 1, again, it's 1 over q minus 1 times a polynomial plus h times a rational function. But you can clean up the polynomial and the rational function. It will look like that. So the polynomial is, again, you go over all classes of degree between 0 and 2g minus 2. That's the interesting part. Q to the dimension, t to the degree. I think that was there before also. I don't remember. And here there were many dels floating around, and now there aren't any dels. If you clean the dels, you get this expression. You get q to the g, t to the 2g minus 1 divided by minus qt. Yeah, I think we had dels here and here, and there are no dels anymore.